Hello everyone, we shall be presenting our work Clustered Wireless Federated Learning RISE 2022 to be held in IIIT Delhi. Now let us begin with what federated learning actually means. A standard machine learning model that most people are familiar with involves a large dataset present on a device. This data is then used to train a model iteratively until we achieve the desired results. But this system has its own pitfalls. To start with, having a large amount of data on one single device is not desirable from a privacy point of view. To create such a large dataset, the data collected from different users will have to be collated together in one place and then made into a dataset. The user privacy is hence violated. For example, consider the case of a hospital. If we wish to make a machine learning model that can accurately detect cancer, we will have to take the data from a large number of cancer patients, collate it, make a dataset, and then train the model on it. So this is not very good for the privacy of the cancer patients. In federated learning, a participating client has its own local dataset on which it trains a model. This local dataset is not visible to anyone other than the client itself. Once the training process is completed, it shares its model parameters with other participating clients. Only the parameters are shared and the privacy of data is maintained. Now consider an algorithm like gradient descent or stochastic gradient descent, which requires a large number of computations. On a very large dataset, this algorithm would take a very long time to train the model and converge. But with smaller datasets distributed among clients, such algorithms can train much faster. In a way, we can say that federated learning introduces the notion of parallelism in the training process. Many clients run the same algorithm parallelly using their own compute resources and send the final updates for aggregation. But now, if we run the federated learning experiment in a wireless setup, we are faced with a number of constraints. To begin with, federated learning in itself is defined by several clients communicating with each other to share the latest model parameters. But wirelessly, the noise is governed by a Gaussian random variable. Now, higher the variance of this Gaussian random variable, higher will be the distortion in the parameter updates. Now, larger the number of clients, larger will be the communication overhead. If any participating client is faced with a bad channel, it will lead to the distortion of the model parameters that it wishes to share with the other clients in the network. This distorted parameter will also affect the global model. Now, if the devices are connected in a decentralized manner, that is, the devices in the graph are connected to each other, the communication bandwidth required will be massive. This would also rise exponentially with the number of devices connected in the underlying network graph. The CWFL algorithm that we have proposed aims to address these issues. In a centralized setting, we require a powerful central server that is capable of aggregating the large number of parameter updates from the large number of clients. In the decentralized setting, we require a very large communication overhead, as I explained earlier. CWFL combines the best of both worlds to provide a setting that is not only much more efficient but also maintains a similar level of accuracy.
So our proposed algorithm, clustered wireless federated learning, essentially clusters a large number of clients on the basis of SNR. So our algorithm is very similar to k-means, where in k-means we use distance as a metric for clustering. In our algorithm, we are using SNR as a metric for clustering. So these are the clusters we obtained using our algorithm on a randomly distributed set of clients. As you can see, within a particular cluster, there are the respective cluster members and a cluster head. A cluster head is essentially that client within the cluster that has the best possible channels with the rest of the clients, and as you can see, it's geographically centrally located within the cluster. So once the clustering phase is done, we can commence the training phase, where in the training phase every client in the cluster will train the local model on the local data set. Alright, so this is like a normal machine learning training procedure. We went one step forward in this phase and we introduced the proximal term, this one, during the training itself within the loss function, that helps in increasing the robustness of the training basically. So this means that the parameter update won't deviate much from the previous parameter value, right? So after the training phase, we have the uplink phase, where every member in the cluster will send their parameter update to the cluster head, for aggregation, standard FL, and then within the when the cluster head will receive all the parameter updates from the respective clients in the cluster, it will aggregate it using some algorithm like FedAvg, for example. Again, the cluster head will receive the model updates through a wireless channel, so the parameter updates would be noisy. But since we did take into account the best channels during the clustering phase, it would mitigate the effect of noise. Alright, so once the cluster head has received all the parameter updates from the respective clients, the cluster heads will communicate amongst themselves in a decentralized manner. That is, every cluster head will send the parameter, averaged out model from its respective cluster and to the rest of the cluster heads for aggregation, right? So now this ensures that all of the data is taken into consideration when the final model is developed. Now that every cluster head has information of the rest of the cluster heads, the downlink phase commences, where now the cluster head will send the aggregated model, the aggregated global model, back to the respective clients within the cluster. So this is our entire iterative training process. This will repeat until the global model converges. So let's look at some results. So the first baseline we would look at is the PAFL, that is the power allocated federated learning, which basically means a centralized federated learning setup where there would be a central server and the rest of the clients would be communicating with the central server, communicating their parameter updates with the central server for aggregation. Now, problem with this kind of setup is obviously the lack of a central server. For example, in D2D systems where highly efficient and a highly powerful central server might not be present, in that case this framework basically fails. So here our CWFL, we can see, performs very similarly to a centralized setting when we take into consideration. So we took 50 clients for training, and when we divide the 50 clients into 3 clusters, we see that maximum accuracy is obtained. So, and even with 4 clusters also, they perform very similarly, 3 and 4 clusters. 5 and 6 clusters converge at a slightly lower accuracy. Now in non-IID data, we can see that CWFL with 3 clusters performs very similarly to PAFL, that is a centralized setting. Yeah, and this is the average accuracy after 50 rounds. So PAFL gives the maximum accuracy as expected, but when we consider a decentralized setting, then CWFL performs very similarly to PAFL. In both IID and in non-IID, CWFL actually performed a bit better than PAFL. Again, we conclude that since we are taking the best channels possible for communicating with the cluster heads, we can see such results.
So this was a brief presentation of our algorithm, Clustered Wireless Federated Learning, or CWFL in short, by myself, Divin, Dominic, and Ayush, Madhan, Sohini from the Intercom lab in IIIT Delhi.